Hello everyone, my name is Ziyang Wang. I'm so happy to be here to introduce our work. The title of our poster is Dual-Contrastive, Dual-Consistency, Dual-Transformer, a semi-supervised approach to medical image segmentation. This work was done by my colleague Congying and I. We contributed equally to this work. In this paper, we are exploring vision transformer for medical image segmentation. Medical image segmentation is very essential for clinical applications, and it is a kind of computer vision task to classify each pixel of an image as to whether it belongs to any region of interest or background. Deep learning has dominated to this area, but the annotation cost for training a model is very expensive, especially in clinical area. It takes a long time and requires a high skill level for clinicians. In this work, we are going to utilize the most recent advanced techniques, including semi-supervised learning, self-supervised learning, and vision transformer to tackle the expensive cost of annotation and also try to achieve better performance. As shown in the top of our poster, we introduce a novel approach to semi-supervised medical image segmentation. It's called Dual-Contrastive, Dual-Consistency Regularization Ensemble Dual Vision Transformer, named 3D-VIT. This method uses the strengths of consistency training and contrastive learning to optimize the utilization of limited annotations. To develop a contrastive learning strategy within a consistency learning framework, the primary goal is to encourage the consistency between subnetworks to the large extent. The 3D VIT incorporates a confidence-aware pseudo-labeling strategy and a robust contrastive learning strategy, both of which are based on domain-adaptive data augmentations. The key contributions has been shown as following. The first one is called dual consistency learning. The introduced dual consistent learning reforms prediction uniformity across subnetworks and attributed input images. For best compatibility with the contrastive learning, assembled pseudo-labels generated via weakly augmented images and masked with a confidence threshold are utilized for unlabeled data. The second one is called dual contrastive learning. We propose an enhanced contrastive learning strategy via two pairs of projectors, seamlessly integrated into semi-supervised framework to boost feature learning performance, which acts on image-level feature maps and explores both labeled and unlabeled data via comparison between weak and strong augmentations. For dual vision transformer, the third contribution, we are motivated by the success of self-attention mechanisms. We investigate vision transformers' potential in segmentation tasks. For a fair and comprehensive comparison, we probe both vision transformer-based and convolutional neural network-based segmentation networks with the same architecture, that is U-shape encoder-decoder style architecture, and diverse learning schemes, showcasing that our proposed 3D VIT outperforms convolutional neural network or combination of convolutional neural network and vision transformer. And we demonstrate in the application study. The framework is robust over diverse combinations of subnetworks, surpassing most selected baseline methods. And for the performance, we evaluated the efficiencies of our proposed 3D VIT on a public cardiac segmentation dataset. Its performance against various existing methods, demonstrating that the 3D VIT outperforms other semi-supervised methods. We conduct our experiments under identical hyperparameter settings and data conditions, employing multiple various evaluation metrics. The code for 3D VIT and all baseline methods are available on the GitHub, and we provide a QR code on the top right-hand side. You can scan it for the details of our framework. And the whole framework is shown in the middle of the poster. Here is a framework image. And the input medical images is on the left, and the output segmentation mask is on the right-hand side. Two vision transformers with two pairs of projectors are in the center of the image. And please note that we denote segmentation inference from unlabeled and labeled data as I and U, and the original images from strong or weak augmented images as S and W. To make it more clear, we denote the sum of loss either by supervised learning, semi-supervised learning, and self-supervised learning, or from labeled data or unlabeled data. It's showing on the right-hand side as the training objective part. For the dual consistency, there are two different consistency learning. One is called consistency under image distribution. It is achieved by high confidence pseudo labeling with the same weak and strong augmentation strategy for contrastive learning. Two networks' prediction on a weakly augmented unlabeled data images are merged and considered as a pseudo label to supervise the predictions of the same image, which is strongly augmented. The pseudo labels are masked and merged to handle the uncertain predictions and stabilize the training procedure with only high confidence predictions utilized, and also increase the consistency of the two networks by using an ensemble pseudo label to improve the performance. And for the consistency on the network distribution, you can see that we achieved it by two different networks. They are initialized separately. Some qualitative results, that is, example images of inference against ground truth, are shown on the figure on the bottom right-hand side. And we use yellow, red, green, and black indicate the true positive, false negative, and true positive pixels. And it shows that our 3D VIT are more likely to predict the true positive and true negative pixels. And for the more quantitative results, they are showing on these three tables. The first table, they are tested on the only 10% of data are labeled, and for the second table, that is different percentage of data are assumed as labeled data, and for the third table, they are just ablation study for consistency and contrastive learning. So in this paper, we propose 3D VIT, a novel contrastive consistency segmentation transformer that effectively use limited annotations for medical image segmentation. And if you have any questions, please do not hesitate to contact me through the email address on the bottom left-hand side, and I also kindly provide the code, and you can just scan the QR code for the more details of our method and also the baseline method. Okay, thank you.